You know when you see a crazy, huge number and just think, there has got to be a better way to write this thing? Well, you're in luck because there is. Today, we're going to get into the tools that let us tame these mathematical giants. We're talking about indices and logarithms. So let that sink in for a minute. A tiny little bacteria culture, growing and growing, and the immense, earth-shaking power of an earthquake. I mean, what could those two things possibly have in common? They sound like they're from completely different worlds, right?
Well, believe it or not, they do. They actually both speak the same secret mathematical language. It's a language that helps us describe incredible patterns of growth and scale. And today, you and I are going to learn the basics of that language. Yep, we're diving into indices and logarithms.
Okay, so let's start with the first part of this whole new language. It's all about one simple idea, making ridiculously big and repetitive numbers small and easy to handle.
So, say hello to the index. You might have also heard it called a power or an exponent. But look, don't let the fancy names scare you off. All it really is a super clever, super convenient mathematical shorthand. I mean, check this out. Instead of writing out 2 times 2 times 2 times 2, which is kind of clunky, right? You can just write 2 to the power of 4. See? It's so much cleaner. It's faster. And trust me, it's way, way easier to deal with when the numbers get seriously big. That little 4 floating up there, that's our hero, the index.
All right, now that we have this awesome new tool, we need to know how to use it, right? Think of this next part as the user manual. There are just a few simple rules, and once you know them, you can unlock its full potential.
Okay, rule number 1. This is what you do when you multiply two numbers that are already in index form. And, this is key, they have the same main number at the bottom.
So, the trick here is as long as the base numbers are the same, like the number 2 in this example, you don't multiply the powers. Nope, you just add them. So 2 to the power of 3 times 2 to the power of 4 becomes 2 to the power of 3 plus 4, which, of course, is 2 to the power of 7. It's such a simple little rule, but it just makes the math so much cleaner.
All right, so that's multiplication. What about its opposite, division? What happens when we divide two numbers with the same base? Let's take a look.
Well, as you probably guessed, if multiplying meant we add the powers, then dividing means we do the exact opposite. We subtract them. It just makes sense, right? So if you look at our example, 2 to the power of 4 divided by 2 to the power of 2, well, that just becomes 2 to the power of 4 minus 2, which simplifies down to 2 squared.
Okay, time for one more essential rule for our toolkit. This one looks a little weird at first. What happens when you have a power that's then raised to another power?
This is what we call the power of a power rule, and it's super simple. You just multiply the two powers together. That's it. So if we have 2 to the 4th, and we take that whole thing and raise it to the 5th power, we just do 4 times 5, and boom, you get 2 to the 20th. This one is a real lifesaver for cleaning up expressions that look super complicated.
So, we've gotten pretty good at building numbers up using these powers. But what if we need to go the other way? What if we need to work backwards? What happens when the power, the exponent itself, is the missing piece of the puzzle?
Up to now, we've been dealing with equations that look like this, right? You've got a base number, you raise it to an exponent, and that gives you an answer. This setup has a name. It's called exponential form.
And this is where things get really interesting. It's easy when we know 2 to the power of 3 is 8. But what if the exponent is the mystery we need to solve? How in the world do we solve something like 3 to the power of t equals 20? We can kind of guess, right? We know 3 squared is 9 and 3 cubed is 27, so t has to be somewhere between 2 and 3. But how do we nail down the exact number? Well, for that, our old tools aren't going to cut it. We need something new.
And that is where the logarithm enters the picture. The best way to think about a logarithm is that it's the opposite of an exponent. They are two sides of the very same coin. It's not some crazy new math. It's just a different way of looking at the exact same relationship. Saying 2 to the power of 3 equals 8 is exactly the same as saying log base 2 of 8 equals 3. The logarithm is the tool that lets us ask the question, what power do I need to raise this base to get that answer? It's how we find the missing piece.
And hey, just like indices had their little user manual, so do logarithms. They have their own set of laws. And what's really cool is you'll see they perfectly mirror the rules we just learned for indices. First up, we have the addition law. This is for when you're adding two logs together. And again, the key is that they have to have the same base.
Now look closely at this pattern. It's the perfect mirror image of our first rule for indices. Remember how multiplying two numbers meant we added their powers? Well, here, adding two logarithms means we multiply their main numbers, what we call the arguments. See that beautiful inverse relationship? It's all connected.
And if you're following that logic, you can probably guess what's coming next, the subtraction law.
Yep, you guessed it. It follows that exact same inverse logic. We already saw that dividing numbers meant we had to subtract their powers. So for logarithms, subtracting two logs means we divide their main numbers. So log base 2 of 21 minus log base 2 of 7 just becomes log base 2 of, well, 21 divided by 7, which is 3.
Okay, enough theory, enough rules. Let's put this new language to the test. It's time to solve a real problem, one that would have been impossible for us just a few minutes ago.
And here we go, we're back where we started, with our growing bacteria culture. This is a classic example of what we call exponential growth. We start with 1 gram, and its mass triples every single hour. The question is, how long will it take to get to 20 grams?
So, first things first, we write out the equation. The mass triples 3 every hour, t, and we want to know when it equals 20. So, 3 to the power of t equals 20. This is that exact problem we were stuck on earlier, but now we have logarithms. We just take the log of both sides of the equation. Thanks to the laws of logarithms, this lets us do something magical. We can pull that t right down from the exponent and put it out front. And from there, it's just some simple algebra. To get t by itself, we just divide the log of 20 by the log of 3.
And when you punch that into a calculator, you get the answer, about 2.73 hours. That's roughly 2 hours and 44 minutes. And just like that, using the power of logarithms, we found that missing exponent. Problem solved.
But here's the really amazing part. This isn't just about bacteria. This mathematical language of growth and scale, it's literally everywhere. It's how your savings account grows with compound interest. It's the pH scale in chemistry, the Richter scale for earthquakes, remember that? And even the decibel scale for sound. So the big question for you is, now that you understand the basics of this powerful language, where else are you going to start seeing it at work?